Hello and welcome. We have spent most of chapter 3 talking about what the first and second derivatives specifically tell us about our original function. We talked about how the first derivative tells us about where our function is increasing and decreasing and where it has relative extrema, and how the second derivative tells us where there are points of inflection, meaning where the concavity is changing from concave up to concave down. So if you think about all the information that we get from those two derivatives, that gives us enough information to create a much more detailed graph than we were able to create in pre-calculus and classes before this class. So let's recap what we know based on the different derivatives and what we know from pre-calc that could help us sketch out a really detailed curve sketch based on a function. So in pre-calc, we learned about domain restrictions, and we reviewed that in this class in chapter P as well. But we talked about how we need to pay attention for vertical asymptotes or holes in the graph. Those are things that we can identify immediately from a function or after a little bit of simplification from a function. And those are things we can easily add to our sketches. In previous courses, we also talked about X-intercepts and Y-intercepts. Those are ordered pairs that we can find to add specific points that we know to be true on our function. And then in previous classes, we've talked about end behaviors such as horizontal asymptotes, or just simply knowing that something to an even power and positive is going up to infinity at its ends, or negative is going down to infinity at its ends, but having an idea in terms of polynomials how they behave at the ends of the function. Then we talked about how our first derivative helps us to identify our critical numbers, and our critical numbers, just as a reminder, are where our first derivative is 0 or where it is undefined. And those values tell us about where it is increasing and where it is decreasing. So with those values, with those critical numbers, we make a number line, and we can identify that our function is increasing anywhere that the derivative is positive, and that it's decreasing anywhere that our first derivative is negative. And talking about how those increasing and decreasing, how it changes, that helps us to identify our relative extrema. Our relative max happens when our first derivative changes from increasing to decreasing, because it would be going up and then it would start going down. That would give us a relative max. And a relative min would happen when we're going from decreasing to increasing. We would then have a relative minimum. Another way that we talked about identifying relative extrema was using the second derivative test. So this can be used for relative extrema. And that tells us that if our second derivative is positive, that would mean that we would have a concave up portion of our graph, which would mean we'd have a relative minimum. So the second derivative test talks about if the first derivative is 0 or undefined, looking at the behavior of the second derivative will tell you the concavity, which will in turn tell you if you have a relative max or min. And then the last thing that we talked about was how to use our second derivative. So our second derivative helps us identify possible points of inflection, and that is where our second derivative is 0 or undefined. And anywhere that that is changing would give us an inflection point. So all of these possibilities are possible inflection points, but we would need to look at a number line to see if it's changing sign to determine if we have an actual inflection point. That number line tells us about concavity. So we know that we have something that is concave upward if our second derivative is positive, and something that is concave downward if our second derivative is negative. So what we're going to do in this video is take all of this information that we've been working on, and we're going to tie it together to create a really good sketch of a function. So we're going to identify those domain restrictions. We're going to look at the end behavior. We're going to identify our critical numbers to figure out where we have increasing, decreasing, and extrema. Then we're going to look at the second derivative to figure out where the concavity is changing and where our function is concave up and concave down. So let's look at this example here. The very first thing we're going to do is just analyze what we could have identified from this function in a pre-calc sense. So looking at this function, it is a polynomial function. In fact, it's a quadratic, which you should be able to graph without using any calculus, but I kind of wanted you to see how it compares using what we know about calculus and not using the algebra. So we know this is a quadratic function, which means we know that its end behavior, since that first term is positive, is that it's going to go to infinity. There are no domain restrictions because we can plug in any x value that we want. There are no horizontal or vertical asymptotes. So really, not a lot of information that we're being given from our pre-calc knowledge. We could find the Y-intercept, which would just be 0, 3. We could compute to find the x-intercept, but let's come back to that portion later. Let's look at the calculus before we worry about finding the x-intercept. Sometimes it's really helpful to do that. Sometimes we may have enough information without it. So let's come back to that. Let's look at the calculus now. If we find our first derivative, we would get 4x minus 4. So where is this equal to 0 when x is 1? So our only critical number is x equals 1. So we're going to make a number line where we plug numbers into our first derivative. So if I plug in something smaller than 1, like 0, I would get negative 4, so I get a negative number. If I plug in something bigger than 1, like 2, I would get 4 times 2 is 8, minus 4 is going to be a positive number. What that means is, and I'm not going to write this out super specifically, but it means a couple of things. It means that we're decreasing from negative infinity to 1, and we know that that is true because our derivative is negative. We're increasing from 1 to infinity. We know that's true because our derivative is positive there. And we know that we are decreasing and then we start increasing, that we have a relative minimum when x is 1. And if x is 1 and we plug 1 in up here, we would get 2 minus 4 plus 3. So that's going to be 5 minus 4, which is going to be 1. So we have a relative min at 1, 1, and we know this is true because f prime is changing. I'm going to use the triangle for change from negative to positive. So I just found another point on my graph, so I'm going to go ahead and graph that point, 1, 1. That's all the information that our first derivative is going to tell us. So I'm going to make some room, and then we're going to find our second derivative and figure out what that's telling us about our graph. Okay, so let's find our second derivative. Our second derivative, if I take the derivative of 4x minus 4, is just going to actually be 4. What that means is, since 4 is positive, our graph is concave up everywhere. There are no points of inflection and no place that it's changing concavity, since there are no points of inflection, which means that our entire graph is going to be cup-shaped. Since we know that this is a quadratic, and we know that this point, 1, 1, is our vertex, we actually know that the axis of symmetry goes through that, which means there will be another point in the exact same spot on the other side. If we didn't remember that, then I would just say that we need a few more points. So I'm going to say find 2 more points in order to make our graph sketch look good. So if we plugged in 2, we would end up getting 3. And let's say we plugged in negative 1. Maybe we wanted a little bit more of a shape. If we plug in negative 1, we would get 2 plus 4 plus 3. So that would be 9. That's not going to fit on our graph. So it looks like these 3 points are going to have to be enough for us to sketch our curve. We know the end behavior is going up forever. So when we connect, it's going to look something like this, which again should look slightly more rounded since it's a quadratic function. So all of this information comes together to help us graph a function. Let's look at a couple more examples. Okay, so here we go on number 1. First of all, this end behavior-wise, this is a polynomial. It is cubic, and the first term is negative. So end behavior-wise, I know it's going to go something like this. I can identify that there are no domain restrictions. I can plug in any x value I want, and that the y-intercept is going to be 0, 2. Now I'm going to find my first derivative. So f prime of x is going to equal negative 3x squared minus 1. And I'm going to figure out where that first derivative is equal to 0. negative 3x squared minus 1. That's going to give me negative 3x squared equals positive 1 if I divide by negative 3. If I try to square root both sides here, I can't do that. I'm going to get an imaginary number. So there's no real solution here, which means there are no critical numbers. Looking at our derivative, no matter what I plug in, I can plug in any one number I want since there's no critical numbers. If I plug in 0, I'm going to get negative. So everything in this entire function is negative. And what that means for our graph is the graph is always decreasing. So it's decreasing from negative infinity to infinity since our first derivative is negative everywhere. Now we need to look at our second derivative. So our second derivative is going to be negative 6x. That's going to be 0 when x is 0. So our possible inflection points are x equals 0. So I can put that on my number line for my second derivative. If I plug in something negative, like negative 1, I'm going to get something positive. If I plug in something positive, I'm going to get something negative. So I do have a change in concavity. This graph is concave up from negative infinity to 0, since our second derivative is positive, and it's concave down from 0 to positive infinity, since our second derivative is negative, which means that we have an inflection point, and we actually do want the ordered pair so that we can graph it. There's an inflection point at 0, and if I go up to my original function and plug 0 in, I get 2. And that actually was already a point on my graph. That's my y-intercept. That's fine. That just means that's where this graph is changing from concave upward to concave downward. So again, right now we only have 1 point on our graph. Let's find a couple more points just so we can get the shape. So find more points. And I'm going to plug in things that are easy to plug in, like negative 1 and positive 1. And I'm going to plug them into my original function. If I plug negative 1 into my original function, I'm going to get 4. And if I plug positive 1 into my original function, I am going to get 0. So I'm going to go ahead and graph those 2 points, negative 1, 4, positive 1, 0. And I'm going to sketch my curve. My curve is going to start opening upward, cupping upward, going through that point and going up forever. At this point, which is my y-intercept, but is also my inflection point, it's going to change from concave up to concave downward because it is my inflection point. All right, I'm going to encourage you to pause the video and get through as much as you can on your own. So first, identify domain restrictions, y-intercept, if there's any asymptotes or other information. Then find your first derivative and analyze the behavior. Then maybe unpause the video and see how you did, and then work through the second derivative. All right, so no domain restrictions. The y-intercept is 0, negative 1. Our derivative is 4x to the 1/3 power minus 4. And if we set that equal to 0, we get our one and only critical number, which is going to be 1. If we plug in something to that derivative that is negative, we will get something negative. Or if you plug in 0, you get negative 4. If we plug in something positive, we would like 2, we would get 2 to something like the 1/3 power times 4. That's going to be bigger than 4. So we would get something positive. So we now know that our function is decreasing from negative infinity to 1, since the derivative is negative, and it's increasing from 1 to infinity since the derivative is positive, which means decreasing to increasing, we have a relative minimum at 1. And if I plug 1 into this original function, I'm going to get 3 minus 4 minus 1, which is going to be negative 2. So I'm going to go ahead and add that point to my graph. So if you got here, I encourage you to pause the video again, find the second derivative and analyze the behavior of the second derivative, and then unpause the video and see how you did. So our second derivative would be 4/3 x to the negative 2/3 power. That's never going to be equal to 0, but the denominator will be 0 if x is equal to 0. So that's our only possible inflection point. So we're going to make a number line with our second derivative, and the only value of interest is 0. So if I plug something negative in there, I'm going to square that, which makes it positive, and then take the cube root and multiply it by something positive. So that's going to be positive. Similarly, if I plug in something positive, I'm going to get something positive out. So there are no points of inflection. This graph is concave up everywhere since the second derivative is positive everywhere. So I know that it's going to be cup-shaped everywhere along the entirety of the graph. Now, in order to make a good sketch, I probably need at least one, if not 2 points. So I'm going to go ahead and find 2 more points. I'm going to plug in -1, and I'm going to plug in 2 to try and get an idea of the shape. If I plug in -1, I'm going to get 6. If I plug in 2, I'm going to get something kind of awful, like 3 times the cube root of 16 minus 9. I don't really want to graph that. If I wanted to find a point on the graph that would work, I need something that cube roots like 8. If I plugged 8 in, I would end up getting 16. That point's not going to fit on my graph. So I'm going to just do the best that I can. -1, 6 is going to be here. And I know that it's going to curve out in this direction really wide, since 8, 16 is a point that would be on this graph. So I'm going to connect. We are concave up everywhere. We were decreasing for that entire interval until I got to 1, and now we're going to start increasing. And I'm going to make sure there's arrows on both ends of my graph. So this is really the whole idea in this video. Can you use all the information that we have been learning to sketch graphs of different types of functions? We're going to sketch 2 more functions in this video. One of them is a rational function, where I'm actually going to give you the first and second derivative to make the math a little bit easier. And the other one is going to be a trig function. So let's get those up on the screen here. All right, here we go. Number 3, we have been given a function, its derivative, and its second derivative. So let's first look at the original function. If you factored that denominator, you would get x minus 1 quantity squared, which means that there is a vertical asymptote in this graph when x is equal to +1, since this would be x minus 1 quantity squared. So vertical asymptote at x equals 1. I'm going to go over to my graph, and I'm going to go ahead and add a dotted line there to represent that asymptote. Now, there is also, if you look at the degree of the numerator and the degree of the denominator is exactly 1 more than the degree of the numerator, so there's a horizontal asymptote at y equals 0. And those are all things that we learned way back in chapter P. Okay, now we need to look at the first derivative, and we need to figure out where it is 0 or undefined. Well, the only place that it's undefined is at x equals 1. And that's not in the domain. So we will include x equals 1 in our number line because we care about how the behavior is changing before and after 1, but 1 is not a critical number. A critical number is now what would make the numerator 0, and that's going to be +1/3 is our only critical number. So I'm going to add that down here. If I plug in numbers like 0, I'm going to get something negative if I'm plugging those into my derivative. If I plug in something between 1 and 1/3, like 1/4, I'm going to get something positive because the numerator is going to be negative and the denominator is going to be negative. So that's going to give me something positive. And then if I plug in something bigger than 1, like 2, the denominator is going to be positive, the numerator is going to be negative, so I'm going to end up with something negative. So now I know that my function is decreasing from -infinity to 1/3 and from 1 to infinity, since our derivative is negative, and it's increasing from 1/3 to 1 since our derivative is positive. I also know that there is a relative min here. There is not a relative extrema here because there is a vertical asymptote. So there's a relative min when x is 1/3. And to save us time, I'm just going to tell you that if you plug 1/3 into your original function up here, you're going to get -9/4. And you can pause the video and work through that yourself and get through that fraction work. You will get the same thing. So I can go ahead and plot that point, 1/3 and -9/4. And I'm also going to go ahead and find the y-intercept, which I should have done but forgot. If I plug in 0, I'm going to get negative 2 over 1. So 0, negative 2 is going to be my y-intercept. Now, why don't you go ahead and figure out where the second derivative is 0 or undefined. So the second derivative is undefined when x is 1, which we've already said there's a vertical asymptote there, so that's not in the function anyways. So if we set the numerator equal to 0, we get that our only possible inflection point is happening at x equals 0. If I plug in something negative, I'm going to get a negative. If I plug in something positive, I'm going to get a positive. So now I can see, and actually I also want to add 1 to this number line. If I plug in something above that, I'm also going to get something positive. So this shows me that my graph is concave down from negative infinity to 0, since the second derivative is negative, and concave up from 0 to infinity, since the second derivative is positive. Now, because of the vertical asymptote in this graph, I probably need to find some more points in order to be able to sketch the shape. I know something's going to be happening to the left of the dotted line and something's the vertical dotted line, and something's going to be happening to the right. So if I plug in one more number to the left, like negative 1, if I plug negative 1 in, I'm going to get negative 5 over 4, so I could plot that point. And this is going to approach both asymptotes. And if we look at our concavity, it's going to be concave down the entire time. And if we look at our increasing, decreasing, it's going to be decreasing until it gets to this red point here. And then it's going to start increasing and going up towards this asymptote. So that red point, which is covered up now, is a relative min. But at that y-intercept is where we are starting to change concavity. And I should have identified that as a point. Where are we changing concavity? When x is 0, so 0, negative 2, is when it starts shifting from being concave down to concave up. All right, I'm going to try and go over that again and make it look a little bit more smooth, but I wanted you to see how it's changing concavity there. There we go. Now, in order to have any sort of graph on the right side of the function, which definitely exists, we're going to need some points on the right side of the function. So let's see what happens when we plug in 2 and when we plug 3 into our original function. Well, if we plug in 2, we're going to end up with 4. If we plug in 3, we're going to end up with 7 over 4. So we're going to have points that look like this. And we know that our graph is approaching both of those asymptotes, that it's decreasing over this entire interval, and that it's concave upward over this entire interval. So there's our graph. We're going to do one last example with sine and cosine, and I really encourage you to pause the video and try and work through this entire problem on your own. See where you get stuck and make a note of that. So this function on number 4 is a combination of sine and cosine, neither of which have any domain restrictions. So our function isn't going to have any domain restrictions. Our first derivative is going to be cosine of x plus sine of x. If you set that equal to 0, you're really asking yourself, when are sine and cosine the same value but opposite in signs? And that they're the same value at our different pi over 4s, but in this quadrant they're both positive. In this quadrant, they're opposite sign, so that's where 3 pi over 4 is coming from. In the third quadrant, they're both negative. In the fourth quadrant, they're opposite in sign, and that's where 7 pi over 4 is coming from. So we have our two critical values for our number line. We know that we're going from 0 to 2 pi, so I'm going to make sure to put those on my number line, because otherwise I kind of forget that I'm supposed to stop and I talk about things going to infinity when we're specifically told that things aren't going to infinity on this problem. If I plug in something between 0 and 3 pi over 4, for example, I could plug in pi over 2, I'm going to get something positive. If I plug in something between 3 pi over 4 and 7 pi over 4, like pi, I'm going to get something negative. And if I plug in something between 7 pi over 4 and 2 pi, I'm going to get something positive. So you may need to pause the video and work through that and really think through your unit circle. But we have now identified that we are increasing from 0 to 3 pi over 4 and from 7 pi over 4 to 2 pi because our derivative is positive. We are decreasing from 3 pi over 4 to 7 pi over 4 since our derivative is negative. And we have a relative max increasing to decreasing. We have a relative max at 3 pi over 4. And if I plug in 3 pi over 4 into my original function, I'm going to end up getting the square root of 2, because what I'm going to get is root 2 over 2 plus root 2 over 2, which is going to be just root 2. We have and that is happening because our derivative is changing from positive to negative. We have a relative minimum at 7 pi over 4. And if I plug in 7 pi over 4, I'm going to get negative root 2. And that's happening because our derivative is changing from negative to positive. So I'm going to go ahead, and also I should find my y-intercept. If I plug in 0, I'm going to get negative 1. So I'm going to go ahead and plot my two extremas and my my y-intercept. And I'm going to choose to make these axes go by 1/2 just so that I can stretch this graph out a little bit. Now, based on the way the axes are here, I know that 3 pi over 4 is going to be halfway between pi over 2 and pi. And root 2 is going to be a little bit more than 1. So I'm going to plot that point right about here. And then 7 pi over 4 is going to be halfway between 3 pi over 2 and 2 pi, and that's going to be down root 2, so down a little bit more than negative 1. Those are going to be my extrema. Now I'm going to find my second derivative. So f double prime of x is going to equal negative sine of x plus cosine of x. If I set that equal to 0, I'm really asking myself, when do sine of x and cosine of x equal the same thing in the same quadrant? So now these are going to be the pi over 4s that I haven't used yet. Pi over 4, they're both positive, and 5 pi over 4, they're both negative. So now I'm going to make a number line with my second derivative. If I plug in something between 0 and pi over 4, like pi over 6, I'm going to get something positive. If I plug in something between pi over 4 and 5 pi over 4, like pi over 2, I'm going to get something negative. And if I plug in something between 5 pi over 4 and 2 pi, like 3 pi over 2, I'm going to get something positive. So I can identify that we are concave up from 0 to pi over 4, and from 5 pi over 4 to 2 pi, since our second derivative is positive, we're concave down from pi over 4 to 5 pi over 4, since our second derivative is negative. And we have an inflection point, two inflection points. Oh, let's do this. I'm going to come up here. We have inflection points at pi over 4 and at 5 pi over 4, since the second derivative changes sign. And I'm going to go ahead and plug those back into my original function to figure out what the y value of those ordered pairs are. And if you plug pi over 4 in, you get root 2 over 2 minus root 2 over 2, which is 0. And if you plug 5 pi over 4 in, you get that they're both negative, and that's going to end up being 0 as well. So pi over 4 is going to be halfway between 0 and pi over 2. 5 pi over 4 is going to be halfway between pi and 3 pi over 2. And those are where we are changing concavity, our points of inflection. So bear with me now as I try and make this graph on my iPad. We are starting concave up until we get here, and then we start turning to be concave down. Then we are concave down until I get to the next purple dot, concave down, and then at that point it starts changing to be concave up again till I hit my next relative min. And then I'm going to curve upwards, and I'm just going to stop somewhere at 2 pi. I guess I could plug in 2 pi and figure out exactly what that value is. And there we have the sketch of our graph. So let's talk about what we covered in this video. The big idea here was tying in what we know from pre-calculus, domain restrictions, asymptotes, intercepts, end behavior, and what we learned in chapter 3, first derivative, increasing, decreasing, relative extrema, second derivative, inflection points, and concavity, to give us a really big picture of what's going on with a function. After finding all of that information and occasionally having to find another point, we can then sketch a very accurate graph of our function. So go ahead and write any questions down that you have, and I look forward to supporting you on this. Thanks for listening.